Okay, so I left you estimating the energy output of a typical galaxy in a year. So recall that a galaxy like the Milky Way, which is a pretty typical galaxy, has about 10 to 11 stars in it. Again, we'll prove that to yourself right at the end of the module. We've said all along that the Sun is a very average star, so why not let's just assume that a galaxy is made up of 10 to 11 suns all shining at the same luminosity as the Sun, and work out how much energy that puts out over an entire year. So we know the luminosity of the Sun, 4 10 to the 26 watts or joules per second. So let's have 10 to 11 of them and scale up by the number of seconds in a year. And that will give us about 10 to the 45 joules. Okay. So recall that we had 10 to the 46 joules being released in a supernova explosion. Okay. So you can see that where supernova might be surpassing that amount of energy. And here's a picture of a supernova going off in another galaxy. Again, we'll see more examples of this later in the module. But here's again, it's a before and after picture. So you can see here this new star has appeared. That's the supernova explosion going off in this galaxy. So it wasn't there before, and here it is now. And you can see the brightness of it. You know, it's comparable to the entire central bulge here. And obviously, this is just in a short exposure. It's going to go on like that for a year. Okay, so let's now focus on what is referred to as the supernova remnant. It's a slightly confusing term, but supernova remnant refers to the ejected material that is left behind by the supernova explosion, not the central object, the core. So let's sort of follow along with what's happening there. As I mentioned just now, then initially that material, all that gravitational potential energy is released during the collapse, and that, you know, the central part goes inwards, but basically the whole outer part of the star gets blown up by all of that energy being injected. And initially it's traveling at thousands of kilometers per second. Over time, that shell of gas, just once you start something going in space, of course, there's very little to actually slow it down and stop it. So once it's been given all that energy, kinetic energy and momentum, it's very difficult to stop. And so this shell will just expand outwards into space, out into the interstellar medium, and it will basically, initially, certainly sweep all before it. It will just push material out of the way because it's smashing into it at high speed. Over time, it will pick up more and more of that interstellar gas that's everywhere in space, and that eventually will start to slow it down. So it'll come up to an average of a few hundred kilometers per second, and eventually, after about 1 million years or so, it will eventually sort of stop. So, as I mentioned here, I'll say this little problem later as to how far it travels over 1 million years, but before it actually stops. But you'll see that this can end up filling up a large volume of a galaxy. Okay. Now, supernovae are quite rare. Okay, remember that massive stars in general are quite rare, so the type 2 explosions that give rise to supernovae are not going to happen that often because there aren't many massive stars around. And the collapsing of a white dwarf in a binary system, it has to be a particular, very close binary system and a particular set of circumstances for that to happen. So they're not that common, but even in a galaxy like our own, it's estimated that a supernova is going off about every 20 or 30 years. Okay. Now, we tend not to see them. In fact, we haven't seen one in our own galaxy in modern times. Reasons for which we'll come to in the next lecture. But they are happening, and so that you've got all of these big expanding shock waves going out through the galaxy all the time. So how do we see any evidence for this kind of hot bubble of gas that's expanding? Well, let's try and estimate its temperature next. Okay. So again, we're just going to do some back of the envelope physics here. So I already just mentioned this term shockwave. Okay, hopefully, you've probably come across that term, but in a sort of physics context, what it actually means is, that something is moving through a medium faster than the speed of sound in that medium. Okay, so a classic example of a shockwave here on the Earth is a supersonic plane traveling through the air faster than the speed of sound, and you get this sort of rumble of a sound shockwave coming out of the plane. Okay, you get the same thing like a bow wave coming off the point of a boat, because the boat is moving faster than the sort of wave speed through the water. So those are examples of shockwaves, and in space you get the same thing. So this supernova remnant that is expanding at hundreds of kilometers per second is much faster than the speed of sound in the cold sort of interstellar atomic hydrogen gas, which remember is only about 100 Kelvin, and so the sound speed in that gas is only about 0.1 kilometers per second. So this stuff is much faster than the sound speed. So when you've got a disturbance coming through that's faster than the speed of sound, the sort of density contrast steepens very quickly into almost a step function, because the gas can't react fast enough. Speed of sound is basically the speed at which pressure tries to equilibrate itself, and it just can't keep up. So you get a shock wave. Now, whenever you get a shock in astrophysics, then it normally tends to heat the gas up to very high temperatures as the fast medium smashes into the cooler medium. Okay, and we can make an estimate of that in a moment. But temperatures are very high, around about 1 million Kelvin, which is very high, of course. Those are the sort of temperatures we met originally when we were talking about the corona around the sun, which is also about 1 million degrees. Okay. And if you remember at the time, then one way to study the solar corona was to look at X-ray wavelengths, where the very hot gas emits strongly, and it's the same here. So you've got very hot gas, okay, 1 million degrees, and it will emit via this mechanism that we've also met before, the so-called Bremsstrahlung mechanism. So this time you've got very hot electrons at 1 million Kelvin, all moving around, interacting with protons. Everything's going to be ionized at these temperatures. And so that same Bremsstrahlung process gives rise to your X-ray emission. Let me get some power before we stop. Okay. So remember, we met Bremsstrahlung before when we were talking about H2 regions, because again we had an ionized gas, but that was only at 10 to the 4 Kelvin, not 10 to the 6 Kelvin. So that factor of 100 in temperature has moved the Bremsstrahlung emission all the way from the radio end of the spectrum all the way at the other end to the X-rays. So let's estimate this temperature. So again, just going to do a simple sort of energy argument here. Let's just assume that all of the kinetic energy from the fast-moving supernova remnant gas, when it hits the interstellar medium, and just turn all of that kinetic energy into thermal energy. Obviously, that's not true because it's not getting totally stopped, but it gives us a good order of magnitude. So, kinetic energy of a gas is half mv squared. Okay, so m would be like the mass of a proton in this case, for instance. and thermal energy. Now, this is something you may not have met, okay, but so you might have to just take it from me. So we're looking at the sort of thermal energy associated with a particle at temperature T. Okay, so if it's just a simple atom, then that will be 3/2 kT, where K is the Boltzmann constant. Okay, so you just have to take my word for that for the moment. I think you may have come across it before, but that, you know, obviously the thermal energy of a gas depends on its temperature, and these are the constants that multiply that. So if we just put some numbers in here, so here's the mass of the proton, okay, 1.7 10 to the minus 27. Let's just take a couple of 100 kilometers per second as a typical speed, and here is the Boltzmann constant, okay, and that gives us 2 million Kelvin, okay. So you can see the idea here, that if you've got fast-moving gas, that is, and you're extracting kinetic energy from it, turning that into thermal energy, then this for those speeds, those are the kind of temperatures you're going to get. So that's where the million-degree gas comes from these fast shock waves moving across the interstellar medium. So let us have a look now again. So we're getting into a much more multi-wavelength part of the module. So these are X-ray images taken by, well, 2 different satellites actually. So there are 2 X-ray satellites up there at the moment. Again, there are links to their pages, I think, on the Learning Resources page in Minerva. So there's XMM Newton, which is the European X-ray satellite, and there are the Chandra is the sort of higher resolution American satellite. Here, both looking at the same object. So the main picture here, you can see this big sort of circle of emission here. So that's the expanding edge of this supernova remnant as it rushes out through the interstellar medium. So there would have been an explosion here some time ago. And this is now the edge where those fast-moving gas is interacting with the interstellar medium. And in the close-up here, the higher resolution view from the Chandra satellite, then you can see it's a very, very sharp edge. So this is classic signature of a sort of shock wave going through space. Okay, the colors here, don't worry about the colors. I mean, they're just telling you where the X-rays are. Okay, so this is pure X-rays. Okay, in this picture, this is a bit of a composite picture. It'll come into focus when I set the little time sequence going. So this is a movie showing you how the fact that these things are moving so fast that you can actually see them moving over a few years. You can see the gases moving outwards over time. So this is a composite X-ray optical image. I think. Let me just start that going. Yeah, so you can see the idea here. So you can see the years clicking over here, and it just repeats. So you can see that everything's moving outwards over time. Okay, so you've got 3 different epochs here. And of course, you can measure the proper motion of these shock waves here. So again, you can see very sharp edges, which is the outer part of the shock, but you've also got these sort of knots of emission here. So they're quite interesting little points of light, and you can just track their motion over time. You know the time difference. If you know how far away the object is, then you can indeed then work out how fast this gas is moving. Okay? So you'll be, needless to say, I'll set you that problem for yourself in a moment. Just while we're looking at this one, you might notice there's an object in the middle of this one, a bright point here. That's because there's a neutron star at the center of these supernova remnants in this case. And this object will be a special type of neutron star that is observed as a pulsar. Now, pulsars are not part of this module. If you want to read about sort of observational evidence for neutron stars, then feel free to have a read about that in the textbook. But it's not, I'm not going to examine any part of that in this module. Okay, So, so that was one famous supernova remnant called Cas-A. Another one, very famous one, is called the Crab Nebula, which is an object you can easily see with a small telescope. If you want to have a look at, again, another movie of the Crab Nebula expanding over time as observed with the Hubble Space Telescope, I would urge you to go and have a look at this link where there's a really nice movie. The crab also has a pulsar in the center of it, and there's some very interesting movies associated with that as well. Again, that's not part of this course, but you can also see the outer parts of the nebula expanding quite nicely in the time sequence there. So if you take the numbers for the Crab Nebula, it has a radius of about 150 arc seconds. Okay, so remember this is arc seconds, and it's about 2 kiloparsecs away from us. Okay. And if you measure the proper motion of those knots of emission in the outer parts of the nebula, they're moving outwards radially from the center with a proper motion of about 0.15 arc seconds per year. Okay, so so that's, again, in the plane of the sky. So you should be able to work out the velocity of the expansion from that in kilometers per second. But another fun thing to do, if you assume that the nebula has been expanding uniformly the whole time at this rate, you can kind of wind the clock back to 0 and work out when the explosion started. Okay, when did the explosion take place? So have a go at that during the break, and we'll see what we get on the other side.